Do you think that AI is taking our jobs?
Oh yeah. Oh yeah. Oh yeah.
Hello, everyone. Welcome to the AI podcast. Today, our guest is Dr. Charles Martin. He is the founder of Calculation Consulting, which is a consultation company that gives machine learning, data science, and deep learning solutions. Today, we're going to discuss open source diagnostic tool for deep neural networks called WeightWatcher, developed by Charles and his team. They have published the research behind this tool in various reputed journals, including Journal of Machine Learning Research and Nature. Charles, welcome to the podcast, and I'll leave the
Hey,
stage to
great.
you.
Thanks for having me. Okay, let me kind of go through the pitch here. Yeah, I run a boutique consulting firm in San Francisco where I support clients building AI and machine learning solutions. I also do some consulting work with the Page family offices on energy and climate, and that work has been kind enough that I can actually support this research. This is a project I started working on several years ago. This is me. So if you need help with AI, I'm the guy. I have an old friend who's a theoretical chemist like me, who's at UC Berkeley, Michael Mahoney, and he was very helpful in helping getting this work started. And so I don't have any formal relationship with the university. However, we're just kind of doing this on the side for fun, and it turned out to work. So we're very excited. So what I'm going to talk to you about is the theory today behind the WeightWatcher tool. So WeightWatcher is an open source tool that allows you to analyze and diagnose problems in a deep neural network simply by looking at the weight matrix. So we don't need any data. There's no training data, no test data. Simply by looking at the correlation structure of the weight matrix, we can learn how well a model is performing. Specifically, we can tell, is the layer well trained? Is it underfit? Is it overfit? Does it have anomalies? So this acts like a data-free diagnostic tool for deep learning. And I think we're probably the only ones that we started this work probably 7 to 8 years ago. So I'm going to kind of go through some of the highlights of where we are now. The idea is that you're going to take a model, some pre-trained model, like Albert or BERT or VGG, ResNet. You're going to look at each individual weight matrix. You're going to do spectral analysis. So you compute the eigenvalues, and then you're going to plot them as a histogram. Okay,
Right.
Not so complicated, right?
Yeah.
When you do that, it turns out there's a huge amount of information in the scale and shape of the eigenvalue histogram, which tells you a lot about your convergence. The way the tool works, it's an open source tool. It's very simple. You just say pip install WeightWatcher. It works currently on PyTorch and Keras models. If people want other models, and it has some basic support for ONNX, but it's not great. If people want other models, let me know. We can add it. We have an open source community on Discord, so people are there doing research and doing pull requests on the tool. So let me know. But it's very simple.
Perfect.
You import WeightWatcher. You give it your model. This might be like Albert or BERT or GPT-3. You say describe. It will give you a data frame, which is basically a description of every single layer. You say analyze, and it will run all sorts of analysis to give you quality metrics on your model. And you can find the code it's on GitHub, on Calculated Content, which is where I work. It's my company, my blog, and WeightWatcher. So as you mentioned, the work has been featured both in JMLR. We have a JMLR paper, which discusses sort of the first pass of the theory, which is implicit self-regularization in deep learning or deep neural networks, evidence from random matrix theory and its implications for learning. So Mike and I did this work several years ago. It was published in June of 2021, but it's actually several years old. Things take forever to publish. Oh, excuse me. Yeah, 21. It takes a while. We also have a paper in Nature Communications. This is an interesting paper. It allows us to predict the model quality, so the quality of a model, your test accuracies or your BLEU scores. We can predict that without looking at the training or the test data. So this paper is probably, I think, the first paper that's come out, which is a meta-analysis of pre-trained models. At the time we did this, again, it's 2021, but this work is several years old, actually. It took forever to get it published. We submitted it to NIPS, we submitted it to ICML, and it's like, they don't understand it. So we submit to Nature. And actually, I was very happy. The reviewers in Nature were very, very good, very professional, very good. But we were the first ones to do this sort of meta-analysis on pre-trained models. And at the time, when I started this research, there were maybe 50 pre-trained models in the world. There was no Hugging Face. Hugging Face didn't really exist.
Right.
Then this paper looked at about 500 different models. About 150 or 200 we were really able to analyze, that scale. Now there are over 50,000 models.
Yep.
So this is sort of like a theory of pre-trained models. So we were not trying to train models, we're just trying to understand them. So we have a number of other papers, we've done talks at KDD, ICML, various papers on the archive. Let me kind of sketch out the basic idea. You take a weight matrix, you plot it, you compute its eigenvalues, and you plot it, you make a log-log plot. So this is log-log scale, this is eigenvalues, this is density. And what you find is in the best trained models, the tail of this distribution on a log-log plot is a straight line. That's a power law. It's a very nice, clean power law distribution. And the way the tool works is it tries to find the start of the tail. So this is where the information, the generalizing components concentrate in the tail. That's one of our conjectures. Or at least you can describe them as if they concentrate in the tail. There may be information out here that's necessary, but you can describe things by looking at the shape of this tail. When you have a good tail, you get a good fit, you get a nice straight line. Sometimes you'll get a bad fit. Sometimes you can't really fit it and you get something kind of goofy. And what the tool does is try to distinguish between when you see good and bad fits. So in some sense, we're just making a simple plot and we're plotting it. Now, we're not doing anything that particularly sophisticated. I mean, you just basically, the tool just loops over the layers. You loop over the layers, you get the weights. They're n by m, or n is Gaussian n. You would compute the correlation matrix and get its eigenvalues. Technically, we do this using SVD. We don't exactly do it this way, but this is in essence what's going on. You're looking at the eigenvalues of the correlation matrix.
Yep.
This is a key idea because we're not looking at W itself. We're looking at its eigenvalues. And then you plot it. So this is really what's going on. The tool automates all this for you, handles different, it gets the normalization right, has all sorts of features. So it's just designed to make this easy for you. Here's an example of what you get as an output. So the idea would be, you have a layer. This is probably VGG, I think, something like that. Yeah, because this is a typical convolutional layer. So you have a bunch of convolutional layers, and then you get the dense layers. So we can handle convolutional and dense layers. Dense layers are easier to analyze. And what you're going to get are these quality metrics. Alpha is the power law exponent. Alpha weighted is a weighted average. It's a scale adjusted power law. You'll get this is the spectral norm. Lambda max is the spectral norm. You'll get these spikes are what I call what we think might be evidence of overfitting. So we get a number of different metrics, and you run the tool, you're going to get this. So let me kind of give you what the theory is doing, like the essence of the theory compared to what other people do, because we're doing something very different than what anybody else does. Like, this is not Pack-Bounds theory. It's not VC theory. It's a little bit like statistical mechanics and theoretical physics, but even there, it's a little different. So typically, this is a typical layer weight matrix. So this might be, say, a layer out of BERT, or it might be the dense layer, FC1 or FC2 in one of the VGG models, something like this. It's just a simple linear layer. If you plot the eigenvalues of this, you're going to find of the correlation matrix, you plot, or the singular value squared of W, you're going to find that they follow this green shape. This is on a log scale, so it's a little easier to see on a log scale. You can see that you get a lot of large eigenvalues out here. This is like 10 to 100. Yep. If you were to randomize W and plot the same thing, you would see a nice simple semicircle. So the the shapes of these curves depend on the shape of W. So the aspect ratio. But the essence here is that this is like W randomized is like the initial guess. it's a random matrix. And because it's a random matrix, it follows the Marchenko-Pasteur or Marchenko-Pasteur laws, and you know the shape of it, and you know that it has a very crisp edge.
Gotcha.
Now, go ahead. You have a question?
No. Yeah.
Okay.
I get it. Yeah.
Right. So the idea here is that the green is very, very different than the red. So you're going to get these tails that come out here. And of course, you're going to get smaller eigenvalues because typically when you train a model, you're trying to preserve the norm. And so you get a very different shape. And the fact that you get this shape, the shape of this green plot is what's really determining the correlation structure. That's our conjecture. And you can see sort of this tail, which kind of peeks out from the red. It kind of sticks out a little bit in here, but this is the tail. This is the heavy tail right here. Now, if you think about what people usually do in statistical learning theory, they don't consider X, they consider W. And they look at W, and you might try to clip the elements, or you might try to bound the spectral norm. And the point is that that's the wrong thing to do, because what you care about are the correlations, not the individual elements. So here's an example of a typical weight matrix. This is, again, this is the layer. I think it's like GP2, of course, it's GP2. So GP2, and you can see that if the spectral density fits a power law. So if you plot a density of the eigenvalues, they scale as lambda to the alpha, to the minus alpha. So alpha is what we call the power law. And typically alpha is between the range of 2 and 6. That's important. This is a critical idea. Smaller alpha is better because you get a longer tail. And the value between 2 and 6 is characteristic of the quality. So typically you should have a small alpha, and the quality of the fit should be good. So we call this is it's a Kolmogorov-Smirnov distance, right? It's a quality metric for the fit. So you want a smallerish alpha between, this range, usually between like 2 and 4. And the quality metric should be good. So if you say watcher.analyze and plot equals true, you can generate all these plots. And what you're going to find, and this is where the empirical data is very important, generally speaking, well-trained layers are heavy-tailed and well-shaped. So and the tool will generate plots on different scales. So we look at different scales, log, linear, log, linear, and the quality metric. And what you'll see is that here, for example, when we try to do the power law fit, this is a good example of what's going on. When you have a really good power law fit, you plot the quality metric versus the start of the tail. So this is X-men in here, this 0 to out here to 100, or in this case 40, 0 to 40, X-men. And you look, if you have a nice convex curve, then the power law fit is really, really good. Sometimes you'll see sort of double minima. And the double minima, we're not quite sure what that indicates yet. We think this might be some evidence of overfitting in the model. And we'll talk about that a little later. But, the quality, both the quality of the fit, this distance, and the shape of this tells you quite a bit. And this is, again, we've tried to do extensive empirical studies. It's not 100%. There are, counterexamples. That's why we create a tool. We want people to use the tool, tell us what the counterexamples are. Here's an example of a comparison of GPT and GPT-2. This is actually in our Nature paper, Nature Communications. You can see that in GPT, the same layer, GPT and GPT-2 are basically the same model, but GPT-2 has more data, so it's trained better. Yep. So here, this layer has an alpha of 4.129, and this is an alpha of 3.393. So that's a fairly big difference. And you can also see that here, the layer is it kind of looks power law, but it has this sort of large outlier eigenvalue here at 100 or so. Here in GPT-2, it's much more filled in. You don't have this giant jump, this spike out here. So
I have a question.
Go ahead.
I have a question on this slide. For instance, what's the significance of the distance matrix and the lambda min? What do they signify?
Lambda min signifies the start of the tail. So the way the power law fit works, the way the algorithm works, is that you have to guess the start of the tail.
Gotcha.
And the tail could be anywhere. So the method, we use a maximum likelihood estimator. It's a standard estimator in statistics, the Closet estimator. Yep. And it tries to find the start of the tail. And it's trying to guess where the generalizing components begin. Like this is where most of the generalization occurs. And so that's what's happening. And later we'll see, like, this is a deep theoretical issue because we can show, using techniques from statistical mechanics and some quantum field theory, we can actually derive where the start of the tail should be exactly. And you can see empirically that it will match when alpha is exactly 2. So there's some deep theory behind it. But right now I'm just trying to give you like to understand qualitatively what's going on.
And the distance matrix?
You mean this? D?
Yeah.
That's a Kolmogorov-Smirnov fit. So that's this value. So as we change the tail, we try to find the optimal tail, and that's it's a criteria for choosing the tail, and it's a quality metric which compares the exact power law the empirical power law distribution to its theoretically exact form.
Okay.
And so it's just a way of finding. It's the standard method used for fitting power law tails to find the start of the tail.
Okay.
Let me give you a comparison between, and by the way, I'll point out a lot of my work is very empirical. We do have a very rich theory behind it, but I'm a physicist. I'm not a machine. I actually have degrees in pure math, physics, and chemistry. I'm not a mathematical theorist. I'm trying to come up with a physics theory. So we do experiments, then we try to come a theory. We try to make predictions with the theory. If the predictions work, we try to make predictions with our theory. When the predictions work, we're happy. When the predictions fail, we go back and try to figure out what's wrong. So here's an example. One of the predictions we have is that, generally speaking, again, this is predicted by the JMLR paper. Generally speaking, smaller alphas should correspond to better generalization. And when you compare GPT versus GPT-2, and you make a plot of all the alphas for every layer, you find that the peak of the distribution, GPT is blue, GPT-2 is red. You find that the peak of the distribution for GPT-2 is smaller than that for GPT. All the alphas for GPT, except maybe this one little outlier, all of them are between, this is probably the embedding matrix, all of them are between 2 and 6, which is predicted by the theory. In GPT, which is a fairly bad model, you can see that the alpha is larger and there are a number of outliers. Outliers meaning that they're not anything above 6 is not a power law. It's just a very, very poorly trained layer.
And that comes from the theory itself, right?
This comes from the theory itself, yes. Yes.
Brilliant. That is crazy.
Yeah. So this is predicted and we saw it. Generally speaking, this is an example we looked at universality. Universality is a concept in physics. The idea that the theory should show a type of critical exponent. So if the theory is correct, we should see that all layers should converge to 2. And we actually can theoretically prove that now. Like that can be proven using statistical mechanics. I can show you that as well. But the idea here was like an early paper. I think this was submitted to ICML. I think this was a poster at ICML 7 years ago or 5 years ago, where we looked at hundreds of matrices. At that time, 500 matrices, 50 architectures. Again, this was way before Hugging Face existed. And we see, that if you look at all the alphas across all these models, most of them are around 2.
Yeah.
They're, but they generally go between 2 and 6. There are outliers. So, and basically this is saying, look, probably a lot of models are not well trained, or there are a lot of layers which aren't that great. But, there could be other reasons for these outliers. We're not sure yet. There could be slack in the model, but this is what we're seeing. So what does the theory say? This is the JMLR paper now. The idea is that when you train a model, you start off with a random matrix. Everybody knows that's how you initialize. You initialize with a Gaussian random matrix, usually with some clipping or something. That's what. As you begin training, you'll start to see, this is a plot of the eigenvalue spectrum. You'll start to see spikes pulling out. And as you continue training, or as you do better and better in generalizing, more spikes begin to pull out. So you see you go from a Gaussian random matrix with a little bit of noise at the edge to something where you have a bulk plus spikes. Now this is sort of smaller, older models, or models that aren't trained that well. Layers that aren't trained that well will begin to look like bulk plus spikes. They'll have a bulk region. There'll be some spikes sticking out. And what we argue is that the spikes contain the dominant generalization components. Again, there can be things inside here which help the model generalize. This is not all noise. I'm just saying this is all we can see. Like using this lens, this is what we see. As you start getting into larger models, more data, larger models, longer training, smaller batch sizes, things that improve generalization, you see the random nature go away and the system becomes heavy-tailed. And at some point, it becomes too heavy-tailed, and we think when it's too heavy-tailed, it's actually overfit. But generally speaking, as you form these tails, this heavy-tailed structure, you see the total matrix becomes heavy-tailed. And what we're doing is just trying to characterize it by looking at this region which is outside the bulk. So the idea is that when you train a model, you see this onset of the strongly correlated behavior. Now, the fact that it's power law, it's not just that it's heavy-tailed, but it's power law heavy-tailed, and it's a good power law. In physics, that's a big deal. It's in machine learning theory, maybe not so much, but in physics, that's characteristic of something very special. So, what does random matrix theory actually say? So, what do our initial weight matrices look like? Random matrix theory says, if I know the shape of the matrix, n by m, I know its ratio. So n is r to n. So it could be 1, could be 2, could be 3. Here's an example of red is 1, blue is 4, and green is 10. If you start off with a square matrix, a square rectangular, but not symmetric, you get something that almost looks heavy-tailed, but in fact, it has this crisp cutoff. There's a crisp cutoff. And this will, if you try to fit this to a power law, you'll maybe get a power law of 6 or 8. So that's the boundary. That's where the boundary is. I think it's 8. I think it's 8 if you try to fit this. As you increase the aspect ratio, as you become more rectangular, the system starts looking more and more like a semicircle, but you always have this crisp edge. So random matrix theory says that there should be a crisp edge. You shouldn't see outliers out here. Like if you're a Q equals, then you should not see these outliers. And also there's a crisp edge on the other side. So you shouldn't see small eigenvalues either. Now, Q equals 1 is a little harder to analyze, but we can talk with it, but it can be done using other techniques. This is what's going on. You have a crisp edge. You shouldn't see, you know where the edges are. So when you see something that's very, very different at the edge, something's wrong. Now, if you actually look at real neural networks, you look at something like, the fully connected layers in AlexNet, and you zoom in. You see, the edge is totally decayed. This is the core. And if you really zoom in, here's FC1, FC2. They look the same. I didn't realize I did. If you zoom in, you see this is power law. It's heavy-tailed all the way through. It's not just decaying at the edge, but the whole shape has been modulated.
Yep.
This is the critical idea. So it's heavy-tailed and power law. Now, some of these ideas really come from when I was a quant at BlackRock. And we were studying correlation matrices of the stock market. And if you're a quant working on Wall Street, you know all this stuff because, the correlation, because you're trying to predict the markets. And the quants on Wall Street are, they're all theoretical physicists. So they've been doing this stuff for decades. And they know that if you look at the stock market, you'll see this sort of heavy-tailed distributions. So what we found is that the weight matrix looks as if it's heavy-tailed. So the idea is that this is the key idea. If W is heavy-tailed, then the spectral density will be heavy-tailed. But the spectral density can be heavy-tailed without W, meaning W can look, if you look at W element-wise, it will look like a random matrix. But if you look at its eigenvalue spectrum, it looks as if it's heavy-tailed. It looks strongly correlated. So all of these pre-trained models display this. And we're going to use it in order to formulate the theory. We're going to use a trick from physics where we are going to pretend that W is heavy-tailed, meaning that it's as if you were to draw W from a Pareto distribution. If you were to draw the elements of W from a Pareto distribution, you would see this behavior. But instead of drawing the elements from the Pareto distribution, we're going to draw the eigenvalues from the Pareto distribution.
Okay.
So again, we've looked at, dozens and hundreds of models. They all look like this, to one extent or another, we think we think the amount of power law structure is a quality metric for the layer. And again, you sort of see that. And in the paper, we talk about this We call it the 5+1 phases of training. So basically, it's a qualitative way of looking at a layer and trying to understand, okay, is it heavy-tailed or not? And the tool, the WeightWatcher tool, will try to do this fit to you, and it will try to help you identify the layers. But the key idea for theory, since you guys are theorists, is that in random matrix theory, this is something that was pointed out in the theoretical physics literature back in the 90s, that there are other universality classes. So typically when you think about random matrix theory, if you look at what people are doing in random matrix theory, you look at the group at Google, like Pennington, or some of the other stuff people do, they typically only think about Gaussian random matrix theory. The elements of W are Gaussian distributed, and because of that, you have this Gaussian random matrix. But it was pointed out many, many years ago in the 90s in theoretical physics that, wait a minute, if W is not Gaussian, you can have other universality classes. And so if you were to draw the elements of W from a Pareto distribution, depending on the tail, in other words, you draw the elements of W from a heavy tail distribution, you would see all these different universality classes. You would see one where if the element you're drawing is mu is the exponent for the Pareto, if mu is greater than 4, there's something called a weakly heavy-tailed universality class. If mu occurs between 2 and 4, then you have this fat-tailed or moderately heavy-tailed universality class. And if mu is less than 2, then you have this very heavy-tailed universality class. And so depending on the structure of the correlations, or in this case, depending on the structure of the heavy-tailedness of W, you see different types of power law distributions. And so the idea of the theory was to say, let's pretend that we can use these universality classes to characterize layers in a neural network.
And
what would it say to us?
And this theory was part of it's part of physics. This universality classes.
Yes, yeah. The idea of universality classes. This idea comes from physics. It's been now proven in mathematics. It was proven, but it was basically developed in theoretical physics to understand strongly correlated systems. Gotcha. And it's widely used in finance. So the guy who did it is a guy named Bouchard. I'm sorry. I don't. My French. I have a French name, but I'm not French. I'm from Ohio. But it was developed by Potters, Bouchard, Gallucci, Mizard, these guys, and they now Bouchard runs a hedge fund in France. So this stuff is used to model the stock market. But the idea is that I can characterize each layer with one of these universality classes.
Interesting.
And there's actually another special universality class that's not in the paper that exists right at 2. So right here, there's this very special this critical universality class, which is actually going to turn out later to be really special. But the idea is that your weight matrices should live in this universality class. And even though the matrix itself is not drawn from a heavy tail distribution, its eigenvalues are. And so it looks like this. And the smaller the conjecture is that the smaller the exponent, the more correlation you have. So it turns out let me show you some empirical data. So then the paper tries to explain a lot of this. But this is one of the key ideas, that there are these universal, and the idea that you can model the correlated structure of a matrix using the universality classes from an uncorrelated theory. That's what we're doing. And there's some deep reasons for that, which because, well, let me just kind of go. I don't want to spend all the whole talk on that part, but you can ask questions. But here I'm going to show you the results. Let's compute we're going to just invent a quality metric. Okay. Let's say I have a model, Albert. Do you know Albert?
Yes.
Albert is a great model. I discovered that one of the guys on our Slack channel suggested this to me. Discord channel. Albert is like BERT, but it only has like 10 layers. And plus an embedding. It's like 9 or 10 layers. I think it's 11 layers. 2 of them are embedding layers. So it has like 9 dense layers, 9 layers. And the way it works is, as you add more data to it and you make the model more complex, the number of layers doesn't change. So you can actually study the actual convergence of the layer as you move from the base to the large to the extra large models. And you can see how each individual layer performs and how the alphas change. So if you just define something still, let's just define something very naive. And let's take the alpha for each layer. So we're going to take each weight matrix, we're going to fit it to a parallel distribution, and we're going to get this alpha exponent. We're going to fit it, we're going to get this alpha for each layer in Albert, and then we're going to take the average. And that should be, and we're going to take the average over all these layers. So in other words, and then we're going to plot the average alpha versus the average model quality. So there's an average model quality you can get. This is all in Hugging Face. You make a plot and you see as alpha gets smaller, the average quality gets better.
Brilliant.
No, it's not perfect, right? I mean, this is the dumbest thing you could do is take an average. So it's not perfect, but it does work. And you can actually monitor, you can see each individual alpha changing.
Yeah.
So this is a really good example of, I think we're the first one, probably the only theory that is theoretical that you can do this, or we're the only ones who can explain why this is going on. So we can make these predictions. Now, this is not published, by the way, but there's a web. I did this for this talk, but I thought it was just such a great model to look at. In the earlier paper, go ahead.
I have one question. Did you guys try to fit it on other BERT models? There are Dilbert, the vanilla.
Oh yeah. Oh yeah.
And it works similarly for everything.
Yes. There's a website called WeightWatcher.ai.
Yeah.
And on WeightWatcher.ai, I try to put many of those examples.
Okay.
So I'm trying to get them all on there. It takes time to, but yeah. So everything is reproduced. So the goal is to make everything reproducible. So to the extent that I'm not trying to recreate Hugging Face. So I expect the models to be somewhere to download them.
Yeah.
So if you can download the model, put them in the tool, and run the plots yourself. So I want everything to be 100% reproducible. And again, there are lots of caveats, right? This is not a perfect theory. I kind of wanted to put this plot to show it works, but there are, why is extra large a little better than XX large? I'm not sure, but I have ideas about that. I sort of suspect that a lot of the very, very large models are widely undertrained. Like, even though they give good quality, I think a lot of the layers are like much bigger than they need to be. And Albert itself the idea of Albert is to make a tiny model, right?
Yeah.
It's like a tiny bird.
Yeah.
Now, in the earlier papers, we were looking at models that change in depth, right? So when you look at VGG, you have to look at like how they change in depth. Well, obviously the metric that correlates with quality is the depth. So that would be useless, if you looked at just the depth. So you have to look at some average. But here it turns out for these models, the alpha doesn't work. You have to scale the alpha by the spectral norm.
Oh.
So you have to take a weighted average. So you have to take a weighted average, which is sort of the log spectral norm, which is the maximum eigenvalue of the layer times alpha. And then you get very good results. And it turns out this actually works better than just looking at the log spectral norm itself. So the log spectral norm actually does correlate with depth. And we discovered that there are some funny things going on, that when you change the depth of a model, you have a sort of funny Simpsons paradox going on. We have a paper on this. We've tried to publish it several times. It's very subtle, but we can see that changing the depth or changing the architecture of a model we think is fundamentally different than just, say, varying the hyperparameters or adding data. Right here, here the width is changing, not the depth. Here the depth is changing. So when the depth is changing or there are other issues, we have this weighted average. So the alpha is just the average, and alpha hat is the weighted average. And maybe I called it hat because I used to be a physicist, right? But so you got to be careful, and then it really should be like weighted alpha.
Yeah. So it's a weighted average of
the layer alphas.
Of the layer alphas, not the normal average thing.
Right. So the original one, alpha is just the regular average, and alpha hat's the layer average. Now it turns out I can derive alpha hats using techniques from statistical physics. So I can actually derive an exact expression for it. And that would be quite surprising, but it can be done. And I can show a little bit of that. Go ahead.
And you have to use this alpha hat when you are sort of experimenting when you are comparing models where the depth is changing for different models.
We think so, yeah. We think so. Yeah, when you're comparing different, when the architecture is changing, the depth is changing, yes. And I would encourage you, if you're trying it, join the Discord channel and ask me, because look, we don't understand everything, right?
Yeah.
We think what's going on. There's also some issues with correlation traps, and that's I have a new theory paper I can send you. So whenever there's a scale anomaly, so I think of it like that. That alpha is a measure of, go to the top here. Alpha is a measure of the shape.
Yeah.
This orange line is X max. It's a measure of the scale. And what we think is happening is that sometimes there are scale anomalies, meaning that sometimes the depth or other problems cause scale anomalies, which, for example, will cause, like in GPT, a large eigenvalue to pop out for some reason. It shouldn't be out there. Why is it there? Like, why is this large eigenvalue here and not close to the rest of them? So there are a lot of weird, funny things. And so the alpha hat tends to adjust for the scale anomalies. And the reason for this is because well, let's leave it at that and we'll move on. I'll show you some other things.
One interesting thing that I noticed about this plot, if you go to slide 27, is that at least the batch normalized models of the same depth has higher alpha hat than with the batch normal. So that's good, right? I mean, that is a good thing. Which means batch normalization is working.
We did the batch normal works. Yeah. It's I'm thanks for pointing that out.
Proof. Yeah.
We can drill into a lot of the details here. There's a lot of detail it's difficult for me to describe, but again, join the Discord channel. I'm happy to describe it. But there's a lot going on. I'll skip that. So alpha hat is like an approximate Shannon norm. So instead of taking, it's like a norm, but you take the norm, the notation's a little goofy, but it's like taking a Shannon norm, where you're looking at, instead of a Frobenius norm, which is you would raise to the 2, you raise it to the alpha power.
Interesting.
Now, in the paper the Nature paper, we go through a variety of sort of meta-analysis of different, here like the ResNets, and you can see, like, as it works really well for ResNet. When you start we've got all the ResNets and you still get a straight line. Obviously, it's not perfect. This is the log Shannon norm. So this is like alpha hat. Log Shannon norm is like alpha hat. And again, we're still working this out, but we see this we're able to predict general trends and generalization. We're able to predict trends and generalization pretty well. It's hard to do, right? I mean, remember, we're not looking at the training data, right? There's no test data. We're just looking at the weight matrices. So we've looked at all these models. We've traded on weight matrices. In the paper, we sort of look at these different, we look at the Frobenius, we compare like 100 pre-trained models. We were able to sub-select and look at various models on various small data sets. Remember, this work is a little old. And we compare various metrics like the Frobenius norm, the spectral norm, weighted alpha norm. So you should realize that other metrics like the Frobenius norm and the spectral norm are not bad. They do work. Like if you just look at the scale of the weight matrix, that's not a bad metric. It's just nowhere as good as what we're doing. Like if you look at the mean squared error, we're way better than these metrics. If you look at R squared, the correlations, so we're way better when it comes to mean squared error. R squared, so we have, depending on how you measure things, we can look about the same or really, really, or worse, or we can look really, really good. So there's some argument about what's the best way to measure generalization, which is fine. So we can also do things like look at the correlation flow. So an example would be, do you want to understand how does information flow through your architecture? So in this case, you would plot the alpha versus the layer ID. And we do this in the Nature Communications paper. And you see that ResNet has sort of a bad information flow. Like this is the layer 0 is near the data. And imagine the labels are out here. And we just kind of show different models to show all the architectures have basically the same flow. They're just some are bigger than others. And you see that in something like ResNet, let's look at ResNet, VGG19. In the VGG models, the correlations get the alpha, the layers converge really well near the data. Converge less, harder to converge. And then when you get these fully connected layers at the end, bam, the fully connected layers recapture the correlation. In the ResNet models, everything is close to 2. All the layers look good. There are little outliers here and there. And then when you get to the end, it's sort of like there's this head at the ResNet model, which we don't know what's going on in the head. Maybe it's underfit, maybe you can replace it. But for the most part, the ResNet models are very, very well correlated.
Yeah, I would hope so, because residual layers usually work better than the vanilla VGG type model, right?
Yes, yes. Yeah, and we can, in our theory, you could see, we're saying you could use our theory to compare different architectures. Of course, they have to be already trained, but you can see the flow.
Interesting.
So it's consistent, right?
Yeah, and when you say that closer to the data, as in when you said that how the data flows from label to the layers, how do you see that in this plot? As in how do you?
Well, I'm just saying, it's the numbering. So if you look at how which layer has the labels, which layer, like where's the like in VGG, the fully connected layers are thought to be sort of at the end.
Yeah,
these are so as you go from like date, you imagine the data's here and the labels here.
I see now. Okay, so you're saying that the last few layers, because they see the labels, they should be close to alpha 2 or
the layer should be close to alpha 2. I'm just showing you how, when you think about information flow, I'm thinking about the data, the information in the training data has to flow to the label to make a prediction.
Awesome. Yeah.
So it's like a flow. Like imagine information, you're concentrating information from the data into the labels. That's sort of we call it a flow.
Yeah.
And you can see in DenseNet, it's all over the place. Like there's no real pattern, right? It's kind of like, it looks a little bit like ResNet, but it's much noisier than the ResNet.
Yeah.
You have too many residuals. So what's happening is there's so many residual connections that information's going all over the place and the system can't converge.
Really interesting.
So other things you can do. Now, this is something which we're working on now to really try to understand better. But this was something, there's a fellow, Xander Dunn, who was working at a hedge fund, and he was using our tool. Our tool is very popular in the hedge fund industry. Because in finance, you can't look at your training, you can't look at the test data. If you look at the test data, you're overfit, right? That's a disaster. So he was using it to see if we can do it you can use the alpha for early stopping. And we had some sort of transformer model he was training, and he found he was plotting the training loss versus the validation loss. And he found that when the validation loss, he gave me these plots, right? I didn't generate these plots. He gave these to me. And he found that when the validation loss went up, alpha crossed 2. That's Brilliant. Exactly predicted by the theory. Wow. I mean, it's exact. Like alpha equals 2. That 2 is the transition point between being heavy-tailed to being very heavy-tailed.
Yeah.
That really shocked me. And we're trying to reproduce this and figure out, is this correct or not? So we've been studying like small multi-layer perceptrons and training them on CFAR to see whether we can reproduce something like this exactly to understand it. But I have a theory paper, in the new theory paper, which is not published, but I'm happy to see your preprint. I actually explain, I show some examples of where when the system will converge exactly to 2, and then when you overfit, it drops below 2. And I have some and actually that's on the website. Actually, you go to the calculated content. I have examples on the website where we have toy examples. Like if you train a multi-layer perceptron on minced, like a really simple model, you get 2 to be the best accuracy, and then when you see a correlation trap, alpha will drop below 2, and it's reproducible.
Nice.
So we have some idea of what's going on, but obviously there's a lot going on, right? There's a lot of phenomena. So we can isolate like bits and pieces. Now, one of the idea of this, the whole idea of this, why in the world do we look at alpha? So this is an idea that comes from, this whole idea started because I read this paper by LeCun, where they were looking at Gaussian random matrix theory to try to understand neural networks. This was years ago. And I looked at this paper, I go, this is total nonsense. I know something about spin glass theory. My advisor worked with Edwards, who has the Nobel Prize for inventing it. I go, this is total nonsense. You can't use Gaussian random matrix theory to describe a correlated system. I remember talking to by the way, my advisor, I don't know if you know this, my advisor is Carl Fried at Chicago. He and John Jumper.
The guy from AlphaFold.
AlphaFold, yeah. So
yeah, I saw that.
Yeah. So I everyone in my group's like, I'm like the runt of the group, Jumper invented AlphaFold. I have another fellow who started Elucidata.ai, so he's leaving all the world's translational medicine. So for me, the bar is, AlphaFold, not solving the generalization theory. So, but the idea is that what we believe is that alpha characterizes the global convexity of what in physics is called an energy landscape. So here I'm showing you the loss landscape, which is a little different than the energy landscape, but there's some work that shows if you look at the loss landscape of ResNet versus a transformer, the ResNet models are more convex. They're sharper, where the transformers are flatter. And there's some papers on this. This is related back to a very old paper in the 90s called Rational Decisions, Random Matrices, and Spin Glasses by Galiucci, Bouchard, and Potters, where they develop a theoretical physics model to characterize the convexity of a random landscape, of a random energy landscape. And the metric they use to characterize it is the power law exponent. So the idea being that when alpha is smaller, you're going to see local, sort of local landscape at the layer, or a global landscape for the model, which is going to be sharper. Yep. And when alpha is larger, it's flatter. So this comes right out of theoretical physics. And it's all in this paper. And in fact, the WeightWatcher theory is a variation of this paper. So the other idea is that when alpha is less than 2, we actually think the layer may be overfit. And again, when alpha is less than 2, this corresponds back to these universality classes. Where are they?
25, I think. It's 25.
25. Yeah, 25. So when alpha is less than 2, it corresponds to being overfit. And again, the new theory, now this, in the new theory paper, and again, it's on my blog, I can show you, I can actually, I can induce an effect called a correlation trap. Basically, you shrink the batch size to 1, you get these weird effects which cause alpha to drop below 2, and you see the test accuracy decreases. So we can actually show this sort of overfitting. So in very simple toy models, I can show this. Generally speaking, if alpha, there are other things that can cause alpha to be less than 2. You can have like I can send you a paper to discuss that. But this is sort of the idea. So we're beginning to just qualitatively see when alpha is less than 2, you're too sharp. And again, these ideas come from the physics literature. We also, other things you want to do with the tool. You can discover what I call scale anomalies. So here's an example in the Nature paper where we look at the maximum eigenvalue, the spectral norm, again, which is not a bad metric, right? It's not completely nuts. And you look at before and after distillation. So we were talking to the group at Intel a few years ago, Intel AI, which is, making these distillation models to put neural networks onto their chips for the cars, right? For self-driving car. And then one of the methods they had come up with, and we discussed this in the paper, the group regularization method, turned out to screw up the spectral norm of one of the layers. And we point this out and go, the alphas are okay, because alpha is scale invariant, but it causes the spectral norm to blow up. And we don't know what the effect of this would be. But sort of the idea of the tool is like, hey, you fine-tuned your model in the sense that you fine-tune it by distilling it. You made it smaller, and you screwed something up. You changed something fundamentally. Would that change the predictions? We don't know, right? But we're sort of like, why? Like, shouldn't it be the same? Why would you change the scale? So there's sort of funny things like that we're looking for. We're trying to look for anomalies in training that we think are corresponding to problems that you cannot see by just doing brute force testing. Right? And that's the idea. Like, you look at a layer and you say, hey, you can always test a model to see if the test accuracy goes down. But you don't know which layer is screwed up. If you don't know what layer is screwed up, how are you going to fix it? So other examples of what I call correlation traps. These are examples of anomalies we see, which we think may be signatures of overfitting. Again, we're not sure. We're still trying to work it out, but we think this is predicted by theory. Again, this is predicted by theory, that as you train a model, you expect the layers to be heavy-tailed, but if you randomize the weight matrix, it should look like a random matrix.
Yep.
It should look, every once in a while you see a rank 1 perturbation. And when you see these rank 1 perturbations in W, it's as if it somehow screws up the correlation structure of the weight matrix and causes the correlations to concentrate around the rank 1 perturbation. You actually see, here's interesting. This is interesting. You see these in BERT, but you don't see them in Albert. They're not there, but they're in BERT. And there's a lot of them. And I sort of have this conjecture that I think some of these very large models like BERT or GPT are memorizing sections of their data. And I think, they're acting like stochastic parrots. And I think we may be able to detect when they do and when they do not memorize sections of their training data by looking at these correlation traps. And that these would be a signature.
If you comment that large language models are memorizing data, that would mean that they're overfitted.
Yes. Yes. But only a little bit. Like they memorize. Like you can go to the WeightWatcher AI site and look at the reports for models like BERT, and you'll see that we don't know what these traps are. I have a theoretical model, and again, I'll send you the paper on it's on the blog, where I show that these traps can induce overfitting, or at least they can screw up the test accuracy. And I have other models where we've seen they actually induce overfitting, but we're not sure yet what they are. They may be, we're just not sure. They may in fact be some. We know that they're not large elements of W. It's not as if you didn't clip W. Like typically to avoid overfitting, you have to clip W, right?
Yeah.
You clip the weight matrix. This is a rank 1 perturbation. It's not a single element of W that's large. It's some funny perturbation, and we're trying. This is a conjecture we have that we think these might be signatures of overfitting. We're trying to figure it out. It's one of this is like where we are today in the research.
Interesting.
And we even have a method, I call it, and the tool will actually clip it out for you. Like you can clip it out, and then like if you see this in your model, there's a tool called SVD sharpness. It will clip it out, and then you can run another version of backprop. You can keep running.
Wow.
It's similar to a pack-bound sharpness transform. But again,
so you train for one pass, and then when you see that there is a correlation trap, you
clip it there, and then you keep training,
and you train from there. Really
that's what we're trying to do. This is what we're trying to do now. We're actually the new release of the tool, which is going to come out in a couple of weeks. We're making everything GPU enabled because it's too slow. We're trying. It's that when I first did this, everything was slow, so running SVD was not a big deal. Doing the power lift, it's now GPUs have gotten so good that I have to make everything. But this is what we're trying. So we have some theories about this. We're testing it. This is sort of the state of the art. What we're trying to do now. And I'm always very open about I open about what we're trying to do theoretically, and if anyone wants to help us, hey, that'd be great. We also have metrics. We have other kinds of metrics. So there's another metric where if you just we want to say how well is a layer correlated. So let's just compare the Jensen-Shannon divergence between the correlated matrix and the randomized version. This turns out to be a pretty good measure of correlation. And it actually correlates pretty well, again, and this is not that's an average, a naive average, not a scale adjusted average. So it turns out just seeing how far away your weight matrix is from random is actually a pretty good measure of how well you're training.
Yeah.
And so there's another paper that's come out in JMLR, and they're trying to use this as a stopping criteria. So they've come up with a way of looking at essentially a cutoff for something similar to the Jensen-Shannon divergence, and they're trying to use that as a stopping criteria for each layer. So this is something you'll see that we suggested on the blog, and then they published it. And then no, we didn't see that on your blog. I go, okay, it's been like on the blog for 3 years. But we give a tool to people, the idea that you might be able to actually do early stopping layer by layer. Like you could train one layer, freeze it, and then let other layers converge. And this is something we're trying to figure out.
Yeah, I have one question. I have one question though. I was hoping that if the RAND distance, which is the distance between the original ESD and the randomized ESD, if RAND distance was smaller, it would mean that the original ESD is very close to the random one. And
yes.
That I was hoping that would cause a lower test accuracy.
Yeah, but it does. No. Test accuracy is small. You're right. Give me a second here.
Yeah, because in this case, I
No, no,
see
no,
that.
no. The larger the RAND distance, the better this plot. I must have screwed something up. I'm sorry. This plot is crazy. Yeah, yeah,
Yeah,
you're absolutely correct. The
yeah,
larger
that's what I
RAND
was.
distance.
Yeah,
Yeah, I don't know what's going on. It's
yeah,
anti-correlated. That is really weird, right?
right. Logically, that would make more sense to me if the distance
No,
was
no, that's what it
higher.
should be. That's what it
Okay,
should be.
yeah,
So there's something
okay,
wrong here. I must have screwed something up.
okay,
It does work. We have a paper where we show that this
yeah,
works, but I must have screwed up I must have put the wrong
okay.
chart.
Okay, at least
All
we're on
right,
the
I got to
same
go
page.
back. That's good. I'm glad you caught that. That's why we're doing this.
Thank you so much. Yeah. Okay.
Yeah,
Yeah.
that's
And,
good. Glad you're
another
paying
question.
attention.
Absolutely. I love this work. Another question I was just wondering about is why did you choose this Jensen-Shannon divergence? Because there are so many divergence matrix that we have, like KL divergence, for instance, which is really used in sort of the deep learning community. So is it like a physics thing, or does it come from computational statistics or some other field of your research?
No, I just picked something I thought would be useful.
Okay.
There's no
Okay. Yeah, okay.
theoretical. There's no deep theoretical reason. I'm just doing try. I just tried it,
Okay.
and again,
Perfect.
it's very strange, right? Because this should be smaller alpha should correspond. Yeah, yeah. See here,
Yeah.
see smaller alpha corresponds to larger distance. I think
Makes
it's
total sense to me.
because I
Yeah.
think it's because the VGG models are anti-correlated. There's no you need this
Mm.
scale adjustment for the VGG model. So I gotta go back
Yeah.
and fix the blog. That's a good point. I
Yeah.
totally missed that.
Yeah.
Um, fix the blog. Yeah, there's something funny about the VGG model, so I'll have to go back. And the other thing about the VGG models is that you have to be very careful because I think the PyTorch VGG models are screwed up because the
Mm.
ones I may have used the wrong model, so that's possible. I thank you for pointing that out. But this
No
is
problem.
the correct plot. You'll see that as the
Yeah.
RAND distance is larger, alphas get smaller.
Brilliant. Yeah.
So
That
yeah,
makes total sense to me now.
right.
Okay.
That's what's going on.
Yeah. Okay.
Now there are cases. Again, this is now you start getting into more subtlety. What you'll find when you run the tool is that sometimes you get really good power law plots, and sometimes you get plots where sometimes it's really easy to detect the power law shape, and sometimes it's hard.
Yeah.
And when it's hard, when it's easy, you'll see if I plot the quality metric versus the start of the tail, so the KS distance versus, you'll see there's clearly a global minimum.
Yeah.
And in cases where it's hard, you'll see there are like two local minima, with a very small barrier between them. And we're trying to understand today better. Now, this only occurs occasionally, but we're trying to understand better why this happens. Sometimes I think what happens is you just get a large anomalous eigenvalue, and the eigenvalue can throw the fit off. And we have some techniques for fixing this. But this is sort of where we are in the research. Like at a gross level, at a coarse grain level, everything works. At a fine grain level, things are tricky, right? So we think we understand generalization at a coarse grain level. At a fine grain level, if you use the tool and you see funny things like this, join the Discord channel and ask me, because, people are asking me now, like, we want to use the tool to do epoch by epoch training. Go, epoch by epoch training? I've been looking at pre-trained models. So epoch by epoch training and trying to understand, can you use it as a regularizer, or can you use it to guide hyperparameter tuning? That's where we are. That's what we're trying to figure out.
Wow.
So we're pretty much convinced we've got the basic ideas right. Now we're getting to like the second order bits. So now I'm going to talk a little bit about what's going on theoretically.
Yeah.
How is this related to neuroscience? So in neuroscience, there's an idea from physics called the critical brain hypothesis. And it was developed by a guy named Prabhak, who unfortunately died early in his life. But he developed a theory called self-organized criticality. And the theory of self-organized criticality is a theory of 1 over F noise. It's a theory that explains why avalanches occur, why earthquakes happen, and how to characterize them. And the idea is that systems that are not driven can still undergo phase transitions. They can change from one phase to another simply by a collection of the way their correlations concentrate. So the idea being that, let's say you have a sand pile, and you're, sort of a kid, you're playing in the sand, and you're making a pile, and you're slowly pouring sand onto the pile. Every once in a while, the pile will collapse. There goes an avalanche. Why does it do that? That's an example of self-organized criticality. The system self-organizes, becomes critical, and then falls apart. So critical states are states between order and chaos. So the idea is that the systems that self-organize will self-organize into a critical state which is stable between order and chaos. Now, this can be seen. The theory predicts that when this happens, you'll be able to fit the spatial temporal dynamics of the system, and they will fit a power law. And if you look at, in particular, the spiking activity of cultured neurons, if you look at neurons, you culture them. These are real neurons now, not PyTorch or Keras. And you study how they spike, and you look at the spatial temporal patterns, and you fit that, you find that they exhibit power law behavior.
Really interesting.
And this is known, and they fit critical exponents. So this is called the critical brain hypothesis. I should have gave this slide first. I'm sorry. I should switch the order of the slides. So what happens is, in simple systems, you see sort of simple behavior. In medium-sized systems, you see power law behavior. And in very large-scale systems, you see truncated power law behavior.
Okay.
The truncated power law behavior is sort of this long tail here. That's truncated. Yeah. So this is a simpler system. This is a complicated system. So what we see in deep neural networks, the idea was that we can look at the static correlations in the weight matrices, and these might look like these sort of snapshots you take of actual spiking neurons. And it turns out they display very similar behavior. And they display not only they fit the power law, they fit the correct universality class. As you get to larger and larger systems, you start seeing truncated power law behavior. So we believe that this is sort of the motivation for what's going on. So it was motivated through neuroscience itself. Yeah. Now, this is just talking about the tool. This is actually deprecated because now we're using Discord now instead of Slack. Now I'll just take a few minutes to talk about the actual theory. I'm going to load another presentation. Give me a second here.
Okay.
Hold on a second. I need to switch the. Well, maybe I can just do it with this. I don't think this will. No, I don't want to do that. Give me a second here.
Yeah, for sure.
I'm going to stop the share and redo it because I need to switch. I thought if I did this in. Okay. And let's share screen again. I need to pick the other. Okay. So the idea here, here's Albert, WeightWatcher. The idea here is that using statistical mechanics, you can derive the alpha hat metric, which is the one that is the general purpose metric that we use. Here we go. So it turns out that, and I have a blog post on this, and we have a paper coming out on it. It turns out that alpha hat can be thought of as a log quality metric, or a log free energy. What in machine learning you might call a likelihood. It's a type of likelihood. It turns out, though, you need to formulate this. I have a paper I show how to formulate this in terms of it's an exact and super free energy. So this is something that comes out of quantum field theory, actually out of quantum gravity. But it's simply an integral over a random matrix. So the idea is that the quality metric is the log of an integral over all correlation matrices times the exponent of the overlap, the trace of the weight matrix with the correlation matrix. So this, I can send you a paper where there's a blog post where I derive all this, but it turns out that alpha hat can be shown to be related to this integral. And this is where it comes from. And this is a direct analogy from that old paper by Gallucci and Bouchard.
Yep.
So the idea is you're going to look at all the correlation matrices that resemble what you see empirically. Now, in order to formulate the theory, and it would take us 4 hours to go, it take us, I don't know, 4 weeks to go through the whole theory. In order to formulate the theory, you have to move from a measure over all random matrices to overall correlated matrices. So you have to do a change of measure. So there's an integral. In order to get to this theory and using statistical mechanics techniques, this is all rigorous, semi-rigorously divided. In order to get to this final integral, you have to do this little step. So in other words, instead of looking at W, you look at W transpose W. And the theory postulates that there's a subspace spanned by the eigenvalues of the tail that where the correlations concentrate. These are the generalizing components concentrate there. Now, again, there can be components out here, just a little subtle. There's just there's a matrix of this rank. There's a matrix of this rank which has these eigenvalues. So how would you test? So the idea being that this measure requires going from mu to d mu of W to d mu of X. There's a Jacobian, there's a transformation, and that Jacobian needs to be 1.
Yeah.
And I can derive this exactly in the paper. We derive this condition. And so the idea being, if you were to look at the eigenvalues of the tail of the distribution, you would expect that if there were some effective matrix describing the correlations, that the determinant of that matrix would be 1. In other words, the sum of the eigenvalues would be 1. Excuse me, the product of the determinant. What the theory would tell you is that, remember before I said we're trying to pick the start of the tail, right? We're trying to figure out where the tail starts. When the theory is correct, when we think that the two theories match, this is a completely different theory, right, from HCSR. So it uses some of the HCSR stuff, but when this purple, so WeightWatcher will actually do this for you. You can run your model. It will produce this plot with a purple line and a red line. The red line is where the Clausius power law estimator says the tail should start. And the purple line is where there's something called the SETOL theory, which is semi-empirical theory of generalization. Semi-empirical theory of learning. The SETOL theory, the purple line says where the tail should start. Okay. It turns out when alpha is about 2, which is when our theory says the layers are perfectly trained.
Yeah.
These two actually empirically overlap. Remarkably. Like, this is quite surprising. There's no reason a priori they should overlap, but they do. And you can run the tool, and I have examples. Here's an example of Albert. In Albert, there's a layer. Not all the layers have alpha equals 2, but for the layers that do have alpha near 2, the purple and red lines are so close you can't tell them apart. In VGG, not all the layers are 2, but it turns out the FC1 layer in VGG 19 has an alpha near 2, and the purple and red lines overlap. And look, that
is because the alpha value for FC1 is closer to 2. Is that
yes?
Is that right?
Yes.
Makes sense. Makes sense.
And I want to point out that FC1 has a correlation trap, as a little bump, and the shapes are very different.
Yeah.
The different aspect, they're very different shapes, right? But the theory still works. So this is now we can derive this. This can be derived, and you can show that this works. And this is, again, it doesn't work everywhere. And I have a tool, and you can try it yourself, and you can see where it works and where it doesn't. So I have a friend on Twitter who's a theoretical physicist, says, calculating something using entirely different techniques from different areas of mathematics and giving the same answer is always lovely. And that's what we've done. We have the HCSR theory, which is in JMLR. We have the new theory, which is all statistical mechanics, and they give the same result. And when alpha equals 2. So that's how I feel about it. So the idea is that there is something special about alpha equals 2.
Yeah.
When you have a weight matrix and you have alpha equals 2, there's something very special that somehow I think that this is sort of this critical exponent, which is where the layer is perfectly trained. It's on the edge of order and chaos. It's on this edge right here where there's this special universality class. We didn't talk about it in the paper, but it is there at 2, where you're between the heavy-tailed, the fat-tailed, and the very heavy-tailed random matrix. And the idea is that this is right between where you're very well trained and where you're overfit. And the theory seems to suggest that, I think we can prove this analytically.
That is awesome.
And that,
So Alpha 2 is sort of like the sweet spot that you want your model to be. So that is the perfect learning, and everything aligns perfectly in terms of different theoretical aspects as well.
yes, it aligns. So this is where we are in the theory. Not there are counterexamples. There are cases where it doesn't work. We don't understand everything, but we think that we're on the right track. And the reason I think we're on the right track is because I was able to derive this independently. Like I was able to derive numerically what's going on. So I think it's the right track. And that's where, and we've released an open source tool and we have a Discord channel. And the idea is that, look, we want people to try the tool, try using the theory in a practical way. Use it. Come back to us. Tell us where it works and where it has problems. And then we can try to figure out what's going on and figure out, is the theory correct? Are we getting the right answer for the right reasons? Are we just curve fitting? Are we fooling ourselves? The only way we are going to know is by working with other people who are trying to train very large models and trying to dig in and figure out what's going on. And that's where we are. And the tool is designed to, that's what we're trying to do with the theory. It's not meant to be, we publish papers, but publishing papers is not the most important thing. The most important thing is to build a tool that people can use to train better models.
100% agree with that.
Right. Yep. It has to have impact.
Yeah.
And that's the presentation.
Thank you so much. Thank you.
Any additional questions?
I do. I just have some general questions that I wanted to ask you. If you want to stop sharing, we can talk about it.
You got it. Give me a second here. I have too many monitors, and let me try to go off. Let me see if I can get my video working. If people want to see me, I'm okay.
Thank you so much for the presentation. It was
Thank
brilliant.
you. I appreciate it.
If you send me your Discord link and your blog post, I will join myself and I'll ask everyone to join your Discord because I definitely want to know more about this. I have some questions regarding some general aspect of the industry, where it's heading as of lately. So my first question is, do you think that AI is taking our jobs?
Oh, yeah. You're going to see a revolution in the back office. Imagine having a large language model that can draft a contract.
Yeah.
Are you going to need a junior attorney? How many will you need? If you're running a legal firm, you need to draft contracts. Drafting contracts is expensive. Imagine having the AI draft, you do the first draft, and then the senior attorney reviews it and makes corrections. That's not 10 years away. That's 10 months away. I have a friend who actually trained, he trained the OpenAI Da Vinci to pass the bar exam.
Wow.
So imagine having, I saw this on Twitter today, a piano that composes music for you. So it just has a few buttons and you sort of press the buttons, like it has like 10 little buttons and you press them and it will actually compose music for you.
Yeah. So,
okay. So I think the AI is going to augment creativity in a way that's going to reduce the amount of manpower necessary to do certain tasks.
So in that case, my question would be, how do we make a sustainable industry where AI and humans can work together?
I mean, I work for a climate change institute. So our policy on this is that sustainability means energy. The cheaper energy is, the more sustainable you're going to be. And I think that, we're big proponents of nuclear power. We should have nuclear power everywhere because it would bring the cost down and eliminate a lot of problems. And you talk about what people are going to do. If we can bring the cost down on a lot of things that we need, then we won't have to work as much. And this is the problem, we're not going to have as much work, as much to do. And I think that, it's not going to be functional unless people can afford to live.
Yeah.
And I think that's where a lot of the issues are going to come up. I mean, certainly, probably a lot of the jobs now are going to be training these models.
Yeah.
I saw a posting on Google for PhD, $50 an hour to help train LLMs.
Wow.
Yeah, it's not a great
That is
rate,
crazy. That's
right?
not a great rate, but I mean,
Not in San Francisco for sure, no, but that's where the future's going. I think a lot of back office work is going. I mean, I don't think things are going to go away, but we're definitely going to see. We need to start thinking about how society will be organized that's different than how we think about what a job is today.
that is correct.
And we need to think of, what does that mean? You know, I'm not talking about socialism or communism. I'm not saying that, you know, and I'm talking about, we need to think about like what we're actually doing. You know, what does energy cost? What do things cost? How are they distributed? We have to think about that in a different way, because they're just, you know, work is going to be large parts of work. We're also seeing an end of globalization.
Yeah.
That's coming. And so, you know, we're going to see more automation at home, but more remote work.
Yeah.
That's a problem, you know, without globalization. So we need to start thinking hard about what that's going to look like. I worked at a company, GLG. I was distinguishing. Every once in a while I get talked into being an employee. I'm not always, and I was distinguished engineer at GLG for a while. GLG had about 1,000 workers whose job it was to use an internal search engine to find people who can answer questions to management consulting contracts. So let's say you're McKinsey or Boston Consulting Group, you come to GLG, you have some complex project you're working on, you're going to ask GLG to find someone to help you with the project. Right. And GLG's business model is that they had 1,000 staff who would talk to the consultant at McKinsey, go to the network of consultants that GLG has, and try to find someone who can do the project. Well, that's not going to take 1,000 people anymore. That might take 20.
Yeah.
Because the AI will do 90% of the work. That's what I was working on. I was there, how to automate that. So it doesn't mean, you know, so people are going to need, so that kind of, I think that kind of back office work, we're going to see a revolution in that.
Interesting. And do you have any comment on the recent lawsuits against generative AI art, especially in Stability AI, and there is a massive outrage among the artist community?
Look, when Google first started, they violated the IP rights of Alta Vista.
Yeah.
And I know the CEO of Alta Vista. And he said to me, look, I don't care if they take our IP. I'll wait till they make a lot of money, and then I'm going to sue them for a fee. And that's what happened. And Google got, you know, Google went big. Yahoo bought Alta Vista, and then Yahoo went to Google and not going to go, excuse me, you're using our IP. You're going to have to pay us 5% for what you're doing. That's how this works. You can't stifle. Innovation's not going to go away. There's a very famous rock star who, you know, from my generation, how old I am, Gene Simmons.
I know Gene Simmons.
The demon, yeah. I love Gene Simmons.
Absolutely.
Right? Yeah.
I love Gene Simmons too.
Yeah, but Gene Simmons was complaining, all these guys are sharing music. There'll never be another Kiss because you'll never be able to get $1 million record contract. Well, yes and no. The music industry sort of died out, and streaming services took over.
Yeah.
So now you pay for streaming. So that's what's going to have to happen. The innovation is not going to stop. You have to change the business model for how creatives work. And that's, you know, obviously there's a lot of IP theft, but, you know, it's not as if, you know, you have to think of a new business model to support creativity. But I think the scarier thing is that creativity is now being augmented.
Yeah.
Right. We augmented, we've got automation with machinery. Then we've automated distribution, right? Distribution's been automated with the internet. You distribute like Spotify. Yep. Now we're beginning to automate creativity.
Yep.
So new business models will be necessary.
Yeah, I think after a point, this field will be regulated. For example, when Google started digitizing books, they used the pages of the images of the books on their website. And when the authors sued Google, they actually won that lawsuit, saying that, hey, we're not earning money from it, even though they were. But
the problem here is that you have regulatory capture.
Yeah.
So when you bring in regulations, you're going to have regulatory capture. The large industries are going to decide what the regulations should be, not because those regulations are good, but because they want to protect themselves.
Absolutely.
And so I think the industries are going to come in and try to regulate it, and the people who innovate are going to try to get around the regulations. There are just cases where you look at, if you let large industry decide what the regulations are, then it stifles, not only it stifles things, but it also be very, very damaging, because they're not regulating to make our lives better. They're regulating to make costs cheaper.
Right.
That's what they're doing. If you look at this, there is so I would be very concerned about regulatory capture, and this is very important that big tech companies actually act in a responsible way. If you go off and do crazy things like censor people on Twitter, the government's eventually going to come in and they're going to run your operation for you.
Yep.
That's you've got to be responsible in what you're doing. If you just do foolish things, other people are going to come in and take it away from you. You're not, so I think we have to be very responsible about this. Look, I have training in nuclear physics. You always in nuclear physics have to think about being responsible. Because proliferation. So this is something which we discuss all the time in the physics community. As a student, you discuss it. We have these sort of discussions all the time. And when I remember 18, 19 years old in freshman physics, we talked about these things. I don't know if these discussions are going on in machine learning or AI classes. Any sense of like what are you actually doing with this technology?
Right.
Because in the end, it has to be the people who are innovating, who are building things, that are responsible in what they do.
Right. Okay. All right. Thank you so much.
That's my two. You got me on. That's my plot. My what do they call it? Soapbox.
Thank you so much. Yeah.
Hey, thank you. I really appreciate the questions, and I'll send you, if you go to the WeightWatcher.ai and go to community, that's the Discord link.
Perfect. Yeah.
So if you want to join, that's great.
Absolutely.
Hey, thanks again. I really appreciate the time.
Thank you so much. Thank you so much for joining the podcast. Have a good one.
My pleasure.
Bye-bye.
Thanks for having me.